In this video, we discuss solving systems of differential equations subject to initial conditions prescribed at t equals 0 using the Laplace transformation method. We're going to start by discussing examples of mathematical models involving systems of differential equations. And then we'll review Kramer's rule, and then we'll do our first example, a relatively simple example. We'll do a more an example that's more involved, which is more likely to show up on a quiz or an exam in our class and in the next video. So we've been talking about solving differential equations all semester. Differential equations often arise from mathematical models. If you describe the physics of some situation and you say that the resultant force is the sum of the forces, what you end up with is a differential equation, usually a second order differential equation, because we think of acceleration as the second derivative of position, right? There are lots and lots of quantities that can be described by differential equations. So we might not actually know what the underlying function is, but we know how its rate of change, the rate of change of that function, is related to the function itself, and maybe even related to the rate of change of the rate of change, a second derivative, and so on. And so we've got this differential equation, and if we can solve it, then we can say something about what's actually going on, that underlying function. Well, with systems of differential equations, what you have is more than one quantity where those quantities affect each other. So you would have what we would call a coupled system of differential equations, or a system of differential equations, which means that one differential equation depends on variables that are described in another differential equation. So when you're solving a system of differential equations, it's kind of like solving a system of equations involving x and y. You're trying to find both the x value and the y value. You're trying to find an xy pair if you're trying to solve a system of linear equations in x and y. Similarly here, we're going to try to find a pair of functions, or maybe a group of functions, x sub 1 through x sub n, that all satisfy these differential equations at the same time. So that's the idea of this. We're going to use a Laplace transform to solve these systems of equations. But before we do that, I wanted to show you at least a couple of examples of mathematical models where you would see systems of differential equations. So here's an example from physics. Let's say you've got an inductor, a resistor, and a capacitor all connected in parallel. And the inductor has inductance L, the resistor has resistance R, and the capacitor has capacitance C. Then the current through the inductor as a function of time and the voltage drop across the capacitor as a function of time satisfy these differential equations. Now, typically, we think of L and R and C as constants. So this is just a constant times V. It turns out that the current, the rate of change of that current through the inductor, is equal to this constant times the voltage drop across the capacitor. And the rate of change of the voltage is equal to this constant times the current through the inductor minus this constant times the voltage drop across the capacitor. So you've got these two differential equations, and these are constants here. So basically we've got this derivative equals a constant times the second variable, and the derivative of the second variable equals a constant times the first variable plus a constant times the second variable. So this is a system of differential equations for I of t and v of t, subject to the initial conditions that at time t equals 0, you have the initial current through the inductor I naught. That's going to be a number. It's going to be known. And at time t equals 0, the voltage at the capacitor is equal to V naught. So you know this and you know this. When you're solving this differential equation subject to these two initial conditions, what you're trying to find is almost an ordered pair. That's how we would typically list it, like x of t and y of t. We're trying to find I of t and v of t. So those depend on t, and the value of I depends on V, and the value of V depends on I. That's why we might think of them as coupled. So this system of differential equations has a solution, which is a pair of functions I of t and v of t that satisfy both differential equations and both initial conditions. Here's another example. It's a very famous example of the predator-prey model. Let's say you have a system that only has two species. We call the first species the prey, that's p sub 1 of t, and the second species p sub 2 of t, that's the predator population. If the net growth rate alpha, where alpha is greater than 0, of the prey in the absence of the predator is proportional to the size of the prey population, then the rate of change of that prey population with respect to time is going to be alpha times the current amount of prey that are there. I always think of the bunnies. If there's plenty of food and there's no predators around, then they just grow exponentially. And that's what this term tells us. Now we've got that's happening. At the same time, the death rate, delta, which is a number and it's greater than 0, and it's known, of the predator population in the absence of prey, if we say that that is proportional to the size of the predator population, so the more predators they are, the higher the death rate is, well, then the rate of change of the predator population with respect to time is a negative times this death rate times the current amount of predators in the population. Now, the predation rate, that's how many times a predator sort of takes down one of the prey. It's proportional to the number of predator-prey interactions, predator-prey encounters. And the number of encounters between two groups is just the product. If I have like 5 girls and 3 guys, the possible pairings, there would be 15 of them, because each of those girls could pair up with each of those guys. So in the same way, the number of predator-prey encounters is just P1 times P2. So that's the predation rate. Now that's going to decrease the rate of change of the population of prey. Every time these guys get together, the population of prey will decrease at a rate beta, which is greater than 0. Now, the birth rate of predators is proportional to the size of its food supply and the size of its own population. So we're saying that this birth rate of predators is jointly proportional to how much food they have to eat and how much of the population they have to reproduce. So that birth rate is gamma. And so we have this rate of change of the predator population is gamma times that sort of number of encounters. And then if we know the initial prey population is this value, and we know the initial predator population is this value, we end up with this coupled system of differential equations. Our goal here would be to find the functions p sub 1 of t and p sub 2 of t. So that's how many predators and how many prey do we have in our environment at a particular time. So we're trying to find those two functions that satisfy both of these at the same time. Now, this is a nonlinear system of equations because you're multiplying those two dependent variables together. Now, it turns out that this does not just apply to, predators and bunnies that they're preying on. It describes other processes in chemistry and economics, and sometimes is referred to as the consumer resource model. So this is a very popular system of differential equations that you would see in other classes as well. Now, I'm not going to go into the details for the other models, but I just wanted to list some of these for you. These were listed in the Constanda differential equations text. So I got these notes from this book by Christian Constanda, Differential Equations, a Primer for Scientists and Engineers. But I just wanted you to see that there actually are systems of differential equations that we would want to solve, where you have two variables, two populations that really depend on each other. They affect each other, and they're described by two differential equations in this case. But it wouldn't necessarily have to be two differential equations. So these are some of the others models that are listed in Dr. Kansanda's book. He talks about military combat. If you have two military forces of strength x of 1 and x of 2, those forces, those strengths of the military forces, x of 1 of t and x of 2 of t, satisfy a certain system of differential equations subject to initial conditions. So we could find those by solving a system of differential equations. Or if you have mixing problems, we looked at mixing problems before, but we were only looking at one tank. If you have one tank over here, and then there's like some kind of pipe and it's connected to a second tank over here, well, the salt in this tank is related to the salt in this tank, depending on, all of the variables in the situation, how much salt is coming in and how much salt is going out and all kinds of things. Well, that would be described by a system of differential equations. And our goal might be to find the amount of salt in the first tank at time t and the amount of salt in the second tank at time t. This one is really interesting. And I thought about covering this, but due to time constraints, we're not going to cover it during the fall 2020 semester. But dealing with epidemics, since we're dealing with the pandemic right now for the coronavirus, this is very appropriate. If S of t is the number of individuals exposed or susceptible to some virus, but they're not yet infected, and I of t is the number of people infected, and R of t is the number of people that are recovered, well, those three functions satisfy a system of three differential equations. And S, I, and R appear in all three differential equations. And then, of course, we can talk about mechanical oscillators. Coupled mechanical oscillators. That's a very fancy way of saying you've got a couple of masses and they're on springs and they're connected to each other. You might be interested in the positions of the first mass and the second mass. We could solve a system of differential equations and find those. So what we're going to do now is solve systems of differential equations. We're not going to go back to the mathematical model. We're not going to try to derive the mathematical models ourselves, but I wanted you to see that this is very much applicable to something, many things, and I'm sure many more things that aren't discussed in that one little section that I just outlined for you from that textbook. But we're going to solve systems of differential equations using the Laplace transformation and using Cramer's rule. So I just wanted to remind you quickly about Cramer's rule. We discussed Cramer's rule back when we discussed variation of parameters. We said that if you have a system of two equations and two unknowns, it looks like this. You have a constant times x plus a constant times y equals a constant. And then a constant times x plus a constant times y equals a constant. And actually, those don't even have to be constants. Those can be functions as they were when we were using variation of parameters. Well, that corresponds to this over here. The coefficients a, b, d, and e, they go in this matrix. If you take this 2 by 2 matrix and you multiply by this column vector, you're just taking dot products. The dot product of this row with this column gives you that value. The dot product of this row with this column gives you that value. So that first dot product is equivalent to that equation. The second dot product equal to that value is equivalent to the second equation. If that determinant, the determinant of this matrix, is not equal to 0, which just means that this system of equations is consistent and it only has one solution rather than having infinitely many solutions or no solutions, then the x value that satisfies this differential or satisfies this linear system of equations is given by this. You just take the determinant of this matrix over here that goes in the denominator, and then in the numerator, you replace the first column in that determinant with that right-hand side. And if that's how you get x. And to get y, which is your second variable, you replace the second column with that right-hand side and otherwise leave it alone. Then if you evaluate this and evaluate this, you can get x and you can get y. And we're going to use this with the Laplace transformation in order to solve systems of equations. It's actually pretty simple and pretty nice. But again, I wanted you to have some context for why we would ever use this. And these are the models. These are the reasons why we might solve a system of equations. So now let's look at an example in which we don't actually know what x and y represent, but remember, when we're solving a system of equations, our goal is to find two functions, x of t and y of t, that satisfy these differential equations at the same time, and those initial conditions. Well, we're going to use the Laplace transformation method for this. The first thing that we want to do is we want to state what our notation is. We start by letting the Laplace transform of x, little x, be big X. I will put little bars on my x of s, just to make it very clear that this is the function of x and this little x is the function of t. And I want the Laplace transform of little y to be big Y, and I'll put a little bar on that y as well, just to make it very obvious. So we'll introduce our notation. And then we'll take the Laplace transformation, or the Laplace transform of both sides of this differential equation. We'll apply the Laplace transformation. And we'll use our initial conditions to simplify. So we'll compute the Laplace transform of the first differential equation, and then we'll compute the Laplace transform of the second differential equation. And I'll just denote that by L of dE1, just as a notational convention for myself to remind myself what I'm doing here. I have the Laplace transform of x prime of t, same as dx dt, right? Equals the Laplace transform of x times 7 minus 4 times the Laplace transform of y. Well, the Laplace transform of x prime is s to the first times big X of s minus little x at 0. And then we'll have 7 times big X of s minus 4 times big Y of s over here. And with my initial condition, I have that x of 0 is equal to 1. And now I want to rewrite this so that I have x and y on the same side and all of the terms that do not involve x of s and y of s on the other side. So I would subtract this 7 times x of s from both sides. So I'd have s minus 7 times x of s plus 4 times y of s. And then if I add that 1 to the other side, that equals 1. So that's my first equation. It's not my solution, but that's my first equation. And then we're going to do the same thing with the second differential equation. So we'll take the Laplace transform of the second differential equation, which is the Laplace transform of dy dt, which can also be written as y prime, equals 8 times the Laplace transform of x of t minus 5 times the Laplace transform of y of t. And that's equal to s to the first times big Y of s minus little y at 0. And that equals 8 times big X of s minus 5 times big Y of s. And then I will use my initial condition to rewrite this guy. Y of 0 is 3. And then I want all of the x's and y's on one side so that I can apply Kramer's rule a little bit. So I'm going to add this 5 times y of s to both sides, and I'll subtract the 8 times x of s from both sides as well. So if I subtract this, I get that, and then the y's will have an s plus 5 if we add that to the other side. And then I'll add 3 to both sides, and I'll get that. And that's the Laplace transform of my second equation. So I've got 2 equations and 2 unknowns, which we could just solve using the methods that we learned about in pre-calculus or college algebra or high school algebra. We could eliminate x of s or y of s and solve for one of those, and then use that one back substitute to solve for the other one. That's one possibility. Or we could use Kramer's rule, and that's what I recommend in this case. So I would say that this system of equations is equivalent to this. My variables are x of s and y of s. On the right-hand side, we have a 1 and a 3, and the coefficient functions are s minus 7 and 4 and negative 8 and s plus 5. Well, then, according to Kramer's rule, x of s is the quotient of these two determinants. First, you take the determinant of this coefficient matrix, and then you replace the first column with the right-hand side. So we'll replace this column with 1 and 3 this time. And that will be x of s. So let's see, what did we do? We computed the Laplace transform of both differential equations, and then we write the system of equations. Well, I guess it's not DEs anymore. Let's just call it the system of equations in matrix form. And then we apply Kramer's rule to find x of s. So in the numerator, we have this. We have s plus 5 minus 3 times 4, which is 12, which simplifies to s minus 7. In the denominator, we have s minus 7 times s plus 5. So it's going to be first times first is s squared. Outer times outer is 5s. Inner times inner is negative 7s. So that's going to be 2s. Last times last is negative 35. And then we're subtracting a negative 32. So we're adding 32 there. So we end up with s squared plus 2s, and negative 35 plus 32 is negative 3. And then we ask ourselves if that factors, and it certainly does. So let's rewrite this with that denominator factored. We have s minus 7 over s squared plus 2s minus 3. And my goal is to take the inverse transform of x of s now in order to get x of t. But in order to do that, I need to rewrite this first. So I will write this denominator as, in its factored form. I need two numbers that multiply to give me negative 3 that add to 2. 3 and 1 will work if 3 is positive and 1 is negative. 3 times negative 1 is negative 3. 3 plus negative 1 is positive 2. And then I see I've got two linear factors. Neither one of them is repeated, so I can use partial fraction decomposition. This is the same as a constant a over s plus 3 over a constant over s minus 1 for some values of those constants a and b. So we're sort of preparing here to compute the inverse transform to get x of t. And that, in this case, it's requiring partial fraction decomposition. And it often does. And then let's simplify. The s plus 3's reduce here, and the s minus 1's reduce here. The s plus 3's reduce here, and the s minus 1's reduce there. And so we get s minus 7 is equal to a times s minus 1 plus b times s plus 3. And since we have two linear factors and neither one of them is repeated, it's really easy to solve for a and b. So we'll just choose the values of s that cause each of these factors to be 0. When s equals 1, this factor is 0. So we'd have 1 minus 7 is negative 6. And that equals a times 0, which is 0, plus b times 1 plus 3, which is 4. So b is negative 6 over 4, which is negative 3 times 2 over 2 times 2. So we get negative 3 over 2. And then to cause the other factor to be 0, we would choose s to equal negative 3. Negative 3 minus 10 is negative 3 minus 7 is negative 10. And then we'll have a times negative 3 minus 1, which is negative 4, plus b times negative 3 plus 3, which is 0. So that's gone. And we get a equals 10 over 4, which is 5 times 2 over 2 times 2, which of course reduces to 5 over 2. So it turns out that x of s is equal to a, which is 5 over 2 over s plus 3, plus b, which is negative 3 over 2 over s minus 1. And that makes it really easy to compute the inverse transform. So then little x of t is the inverse transform of capital X of s. And that's going to give me a 5 over 2. This is 5 over 2 times 1 over s plus 3. So I'm comparing that s plus 3 to s minus a, so a is negative 3. And I'm comparing this s minus 1 to s minus a, so a is 1 here. The inverse transform of 1 over s minus a is e to the at. So we'll have e to the negative 3t for the first one. Then we bring our constant negative 3 over 2 down. And then we have e to the t for the second one. So that's x of t. And we're trying to solve the system of equations subject to those initial conditions. So we've got x. We could use x to find y using these differential equations if we wanted to. You could just take the derivative of x and plug in x here and then just solve for y. That's one option. Or we can use Cramer's rule again. I would recommend using Cramer's rule again. So we're going to do the same thing that we did here, but instead of replacing the first column with 1 and 3, we're going to replace the second column with 1 and 3. And that denominator is exactly the same. It's still s squared plus 2s minus 3 for our y of s. So let's do that. So by Cramer's rule, y of s is equal to this. And my matrix was s minus 7, 4, negative 8, and s plus 5. And I'm going to replace my second column with 1 and 3. That is this column on the right-hand side of our system of equations. And we leave the first column alone. If I distribute, if I multiply across this diagonal, multiply by 3, I get 3 times s minus 21 minus a negative 8, so that's plus 8, all over whatever this is, which we know, because we've already done the work, that is s squared plus 2s minus 3. Well, negative 21 plus 8 is negative 13. And we can use partial fraction decomposition again because we're trying to find y of t. So I would write that as 3s minus 13 over s plus 3 times s minus 1. And that equals a over s plus 3 plus b over s minus 1. Multiply by the LCD, don't forget your parentheses there. The s plus 3's reduce, the s minus 1's reduce, the s plus 3's reduce, the s minus 1's reduce, and we end up with this. We end up with 3s minus 13 equals a times s minus 1 plus b times s plus 3 in order to find A and B, we just choose the values of S that cause each of these factors to be 0. So when S equals 1, this factor is 0. So we'll have 3 minus 13, which is negative 10, equals A times 0, which is 0, plus B times 1 plus 3, which is 4. So we'll have B equals negative 10 over 4, which is negative 5 times 2 over 2 times 2. So we have negative 5 over 2 there. And then when S is equal to negative 3, this factor is 0. So I'll have negative 3 times 3 is negative 9. Negative 9 minus 13 is negative 22. And this will be A times negative 4 plus B times 0. So I'll have A equals 22 over 4, which is 2 times 11 over 2 times 2. So A is 11 over 2. So what we have here is y of S equals A over S plus 3. So that's 11 over 2 over S plus 3 plus B. And since B is negative, I could just say minus 5 over 2 over S minus 1. And that means if I take the inverse transform of this, I get y of t. Here, A is negative 3. If we're matching that pattern, 1 over S minus A, here A is 1. So we have y of t equals 11 over 2 times e to the negative 3t minus 5 over 2 times e to the t. And the solution to our system of equations is x of t, y of t, where x of t is 5 over 2 e to the negative 3t minus 3 over 2 e to the t, and y is 11 over 2 e to the negative 3t minus 5 over 2 e to the t. I'm not going to check it in this video, but you could check it if you wanted to. You could take the derivative of each of these equations and substitute x and y into the left-hand side of the differential equations. And hopefully the derivative of x of t is equal to this, and the derivative of y of t is equal to this. And then if we evaluate both of those functions at t equals 0, x of t should be 1 and y should be 3. Let me just check the initial conditions. If I plug in t equals 0 here, I get 5 over 2 minus 3 over 2, which is 2 over 2, which is 1. That's good. And then over here, if we plug in t equals 0, we'll have 11 over 2 minus 5 over 2. That's going to be 6 over 2, which is 3. That's good. So the initial conditions are satisfied. The only other thing we would need to check is that these two functions satisfy both the differential equations at the same time. But you can do that if you want to verify our solution. Okay, so let's just walk through the method one more time. You introduce your notation. You take the Laplace transform of the first dE and the Laplace transform of the second dE. Then you rearrange those so that you end up with a function of s times x of s plus a function of s times y of s equals a function of s potentially. And you do that to both of them so that eventually you can get down to a system like this. So you've got your coefficient times your variable plus a coefficient times the variable equals a function. And then you've got your coefficient times your variable plus a coefficient times your variable equals a function. Then you list the coefficients in this matrix here. This 2 by 2 matrix times this column vector is equal to that vector over there. Then you can easily use Kramer's rule to solve for the Laplace transform of x of s. Then you compute the inverse transform. Then from there, you have some options. You could use x of t to find y of t by substituting x of t into this first differential equation and solving for y. That's a possibility. Or you can use Kramer's rule again. So I chose to use Kramer's rule to find y of s as well. And then of course you want to write that in a form where it's easy to take the inverse transform. So we had to do some partial fractions. And then once you do that, you compute the inverse transform of y of s in order to get y of t. And then the solution to a system is A system of two equations with two unknown functions x of t and y of t is an ordered pair x of t, y of t. Two functions of t that satisfy both equations and both initial conditions